I'd like to show you how to work through a psychrometric problem. In other words, a mixture of dry air and water vapor, very common, the type of mixture that we breathe in every day. It's our surroundings, a mixture of dry air and water vapor. Would like to show you how to use the psychrometric chart to solve a homework problem, hopefully that's been assigned to you. But let's go ahead and get started to give you some tips on how to read what could be a pretty confusing chart. This is going to be problem 1237. So let's look at what we're assigned to find. 1237 says, solve problem 1231 using psychrometric chart. Okay, fair enough. A good purpose of this problem is to show you how quickly you can solve a basic atmospheric air problem if you know how to use the psychrometric chart far faster than if you have to go back to fundamental principles and use the steam tables to look up properties and do a lot of detailed calculations. So if you get good at being able to read the psychrometric chart, that can benefit you. And also, especially if you're simply assigned to use the psychrometric chart. It says a lecture hall now it has a volume of 1 million cubic feet. That is a big lecture hall. So that's even going to be bigger than the typical classrooms that you might have in Goodwin Hall. Not as big as the Burris Hall Auditorium, but a very large lecture hall. It contains air at 80 degrees F, 1 atmosphere, and a humidity ratio of 0.01 pounds mass of water vapor per pound mass of dry air. And the assignment is determine the relative humidity. That's an easy question. The dew point temperature and the mass of the water vapor contained in this big lecture hall room. So let's go ahead and get started. If you want to get a little better feel for what's going on with psychrometric mixtures, now, of course, the psychrometric chart is going to apply to mixtures at 1 atmosphere. But if you can go in and do the detailed calculations, you can perform the detailed calculations at any ambient pressure. But I want to chase you, hopefully, to at least browse my atmospheric air 01 and atmospheric air 02, those two videos that are in my playlist called Example Problems Psychrometrics. And that can give you, hopefully, a working understanding, a working knowledge of what these atmospheric air-water mixtures are all about. A quick note before we start into the psychrometric chart about understanding the variable called humidity ratio. That's Greek letter omega. That's not W. It's Greek letter omega. And the definition of humidity ratio for a mixture is the mass of the vapor in the mixture divided by the mass of the dry air in the mixture. In other words, that nitrogen, oxygen, ideal gas. Okay. And so so that's the words. So that's equal to m sub v. That's the mass of the vapor divided by the mass of the dry air. Now, recognize that humidity ratio omega is not a dimensionless number. In the numerator is pounds mass of vapor. In the denominator is pounds mass of dry air. So those are two different substances. And so please do recognize that omega, humidity ratio, it's a ratio. It is not a percentage. In other words, it's not dimensionless. And so the units are pounds mass per pound mass, except it's pound mass of vapor divided by pound mass of dry air, or in SI, kilograms of vapor per kilograms of dry air. Okay, so let's plan what we're going to do before we go out and do it. The first thing we're going to do is we have some given information, so we have enough given information to pinpoint the state of the room on our chart, on our psychrometric chart. We're just going to plop a black dot down That'll be our state. The next thing we're going to do is read off the relative humidity from the chart. And it's going to be just like that. Boom, we've got a number for relative humidity. A very important number, right? So the higher the relative humidity, the more clammy you feel, the more humid it feels. When relative humidity is low, kind of like in Arizona, air's nice and dry. It doesn't feel so clammy, right? So the relative humidity value, it's an important from a personal standpoint. We're going to be able to read off the dew point directly from the chart. What does the dew point do you? Well, that tells you that if you're out and your mixture cools down, if things cool down, at what temperature will water start to form? In other words, if you're out on the golf course, at what point would dew start forming on the grass as your atmospheric mixture cools down? The next thing we're going to do is read off little v of the dry air, the specific volume of the dry air from the chart. And the reason we're going to do that is that we're asked to find the mass of the dry air, of the vapor, I'm sorry. So if we can find the mass of the dry air first, we'll use the mass of the dry air is the volume, 1,000,000 cubic feet, divided by the specific volume of the dry air. We've got the mass of the dry air. And then we've got the humidity ratio given 0.01 pounds of vapor per pound of dry air. Then it's a child's play to get the mass of the vapor from the mass of the vapor is omega humidity ratio times the mass of dry air. Simple as that. So that's where we're headed. So now let's go on to our psychrometric chart. So step one, pinpoint the state. How are we going to do that? Okay, let's see what we got. Let's look at the x-axis first, and the x-axis says dry bulb temperature. Now, what's that? What's dry bulb all about? Well, that's sort of back the throwback days of thermometers that had. So this is a thermometer I got off my wall, and it's the red stuff in there. It's alcohol that's dyed red. Okay, and here we go. And so you see that this is the bulb of the thermometer, okay? And of course, you see that it's dry. It's just sitting out in the air. It's dry. It's not sunk in water or anything like that. That's why we call it the dry bulb temperature. So that's the x-axis. So all we got to do is find 80. So we know we're on this 80 line somewhere. The y-axis. The y-axis is the humidity ratio, which for this problem is given 0.01. So we go find it. So our state is going to be along this horizontal line. So the intersection of those two lines, vertical and horizontal, is that black dot. Just put a black dot there. Okay. So we have pinpointed our state, the state of our mixture on the psychrometric chart. The next thing we're going to do is read off the relative humidity. So there's all these curves. We got to do this with our eyes. So I've made our black dot a little bigger and fatter just for sort of effect. So there's our black dot. And you've got to start studying on your psychrometric chart. And so notice down here, you see these curves. There's some curves that are swooping upwards. And you see how they're labeled relative humidity. And let's look numerically what the relative humidity numbers are: 10, 20, 30, 40, 50, 60, all the way up to 90. And then on this line, 100%. That's rain, okay? So that's going to be where water starts falling out of the mixture, fully saturated. Okay, so here's our dot. And so at least starting out, can you see about what is our relative humidity? It's somewhere between 40 and 50%. So we've got to teach ourselves to be to calibrate our eyes. It is tough. And of course, you're not going to get 4 significant figures in your result. Okay. And in fact, when I calibrate my eye and I shrunk my big black dot down to something a little more reasonable, and I try to do my best to interpolate by eye between 40 and 50, I get a relative humidity of 45%. So that's what I write down on my solution, 45% relative humidity. Next, we're going to work on the dew point. So first, what is the dew point in words first? So here's our point. And so to get to the dew point, what you do, and this is right out of reading your textbook reading, doing some of the computational problems, very good example problem in the book, as well as in my own, I think, Atmos Air O2. I give a worked out example numerically to show that the way you determine the dew point and physically what happens in the real world is the mixture is cooled, remove heat, at constant partial pressure until water starts to condense out of the mixture. In other words, dew forms on the grass. Okay. If you do some thinking, you can satisfy yourself that cooling at constant partial pressure is the same as cooling at constant humidity ratio. Do you remember in your book that humidity ratio, there was a formula derived for humidity ratio? It was 0.622 times the numerator is P sub V, partial pressure of the vapor, divided by denominator, partial pressure of the dry air. Okay, so if you study on that derived relationship, you can satisfy yourself that to get to the dew point, you're cooling at constant omega. So so now we're going to get somewhere. Do you see that we're cooling? So what's constant omega? That is a horizontal line. Constant humidity ratio. See, here's our humidity ratio on the y-axis. So we're cooling across a horizontal line. So I'm going to go to the next slide. Okay. So here we go. Here's our state. We draw a horizontal line until the horizontal line exactly hits this saturation line. So I didn't put a dot there. I wish I had put a dot there, but imagine putting a dot there. Can you see what is the dew point temperature? Well, this kind of diagonal axis says wet bulb or saturation temperature. For our case, the saturation temperature is the dew point temperature, and it's somewhere between 50 and 60. Now, you've really got to calibrate your eyes here because you've got to study on this. The 50 corresponds to this dark blue line here, not these light blue lines up here. That's something different we'll talk about at a different time. 60, that corresponds to this dark blue diagonal line here. And so the lighter blue line, diagonal lines are equally spaced between the dark blue. All right, so you can study on that, and you can see that if I were to put my dot where I'm squiggling my cursor, with your calibrated eye, you would get 57 degrees F. So in my solution, I'm going to write down the temperature of the dew point is 57 degrees F. That takes a little practice to get good at that. Let's move along. The next thing we need to do is read the specific volume, little v, of the dry air. Here's our state. So we've got to start shopping around. Where am I going to get specific volume? And I'll have to tell you, I had a little tough time finding this after it had been years since I used a psychrometric chart. Here it is. Here's these diagonal lines here are labeled specific volume, cubic feet per pound mass of dry air. And let's look numerically. What are they? Up here is 15, 14, and 13. That corresponds to these darker diagonal lines that are swooping downwards. Here's our state. So do you see that at least at first glance, our V, our specific volume of dry air, is going to be somewhere between 13 and 14. So we got to do that calibration again, and at least we see that these lighter blue diagonal lines are equally spaced between the darker lines, and then there's that's correct, yeah. And I had to do some studying, right? So I had to be very careful. And what I came up with my calibrated eyes, I'm going to say that the specific volume of the dry air, so you know it's going to be closer to 14 than 13. At least you got that far. I'm saying the specific volume is 13.85 cubic feet per pound mass of dry air. 13.85. So that's what I'm writing down in my solution. Okay, so now we're done with the psychrometric chart. We got some very simple computations to do. Our room volume is 1,000,000 cubic feet. We found from the psychrometric chart the specific volume of dry air is 13.85 cubic feet per pound mass. So we just used the definition of specific volume to get the mass of the dry air is 72,000 pounds mass. That's a high mass of air, isn't it? But it's a big, big lecture hall. Then we're going to write down our humidity ratio, which was given 0.010 pounds of vapor per dry air. Just by inspection, then you can see that the units are going to get our units right, we multiply 0.01 by 72,000 to get 722 pounds mass of vapor floating around in the lecture hall in the air vapor mixture. And a lot of times in these problems, it pays to summarize your work. And I've summarized my work here. Relative humidity, 45%. Dew point temperature, 57 degrees F. And we've got a mass of the vapor of 722 pounds mass. Now, so I got to tell you, say, God, what a waste of time, because we're only getting we're not getting 4 or 5 significant figures here. I'll tell you that these psychrometric charts can really speed engineering calculations for those people who are involved in heating, ventilating, and air conditioning engineering problems. There are entire careers associated with engineers working on HVAC situations. It's a big, huge industry. It goes all the way from home heating and cooling to commercial building heating and cooling, industrial heating and cooling, aircraft cockpit heating and cooling. You get the idea. So these psychrometric charts can pay off for the engineer with a little experience. So let's recap a little bit. For this problem, this chapter 12 problem, you really need to understand the basic definitions of mixtures to get good at this. You have to understand the fundamentals of the definitions and fundamental of specific volume, things like that. So I do think you can see for this situation, blindly using some type of formula, that's a losing proposition. For these mixture problems, psychrometric problems, atmospheric air vapor mixtures, watch your units of dry air versus mixture units. That's a key. That's a key to success, is recognizing the difference between dry air and the mixture of air and vapor. And of course, express results, including your units. So that's a quick step through how to get better and better at using the psychrometric chart, preparing for quizzes and tests. Depending on your instructor may require you to solve a problem using the psychrometric chart in a quiz and test. So of course you want to be prepared for that. And also you need to prepare yourself to do the detailed computations as well. But you can see that it's a huge time saver, but also in a quiz and test situation, it can be a requirement depending on your instructor. So I hope that helps. I hope that gets you a little better, gives you an introduction into, gosh, where do I start? Here's this crazy looking graph or chart that I've never seen anything like that before. I never had seen anything like that before until I took the thermodynamics class, and I had to work pretty hard to figure out, to make some sense of it. I ended up depending on some students that had been through it before, some of my fellow students, to get better and better at it. So I hope that helps, and hope to see you next time on some of these other worked out homework problems.